Good morning. I'd like to talk a little bit about buffering solutions today, or buffers as we know them. If you think about the word buffer itself, it means that it's kind of protecting you from changes. So you can kind of think about like bumpers in bowling, right? When you put the bumpers up in the lane and you're protecting the ball from going into the gutters on either side, right? A buffering system is kind of the same way, but from a chemical standpoint. So we call these buffers then solutions that are made up of a weak acid and its conjugate base, or vice versa. So we could have a weak acid or a weak base and its conjugate acid, which is why it's so important to know those Bronsted-Lowry acid-base conjugate pairs, because if we see a system that has those, then we know that it can have a buffering capacity, a buffering capability. And how well a buffer can act as a buffer is called the capacity of that buffer. And really what that means is how well it can resist a large swing in pH values when either a strong acid or a strong base is added to the system. Now, buffers are really important in biological systems because there are certain proteins and there's certain biological functions that can only happen under certain very tight pH ranges. So we have specific pHs in our bodies, and any sort of biological organism is going to have specific pH ranges that their proteins can work in, that their enzymes are going to function in. And so these buffering systems are in place in order to allow for processes to occur. And we can exploit them as chemists then by creating a buffering system with specific characteristics based on kind of what we know about the different acid-base pairs and their weak acid or weak base equilibrium, because that's what this is all about. It's all about Le Chatelier's principle. So we remember that one, which if you've seen any of my videos before about equilibrium, and if I've talked about Le Chatelier's principle before, I always call that the nature finds a way principle, or the Jurassic Park principle, right? It says that if I have a system in equilibrium and I do something to mess with it, so if I disrupt the equilibrium, then that system is going to shift in such a way to where it restores the equilibrium and creates a new equilibrium. So anything that's going to disrupt an equilibrium is something that's going to mess with the rate of the forward or the reverse reaction. Because we know that that's the definition of dynamic equilibrium, that the rates of two opposing processes are equal. So let's think about that Le Chatelier's principle with just a weak acid kind of system. Now I'm leaving the water out of this. It's there, and we know it's there because all of my species here are aqueous or aqueous. So we would have water on this side. We know that we can kind of ignore the water because it's not going to be part of our equilibrium constant expression for this, right? Because it's a pure substance, so we can't talk about the concentration of pure water. And so instead of hydronium then, because I don't have the actual chemical formula for water in here, I have the hydrogen. But we know that hydrogen in an aqueous solution is in the form of H3O+, or hydronium. So let's say that HA here is a weak acid. And we would know that it's weak based on its Ka value or based on the way that it behaves in solution. If we were looking at the Ka value for this particular reaction, if it's quite small, that means that I have more of this than I do of this, which means it's not really acting very well like an acid, right? The definition of an acid is something that puts hydrogen or hydronium in solution. And if it doesn't do that very well, if it only partially dissociates, then it's on the weak side. And the degree of weakness then is going to be based on our equilibrium constant. Now, the weak acid has a relationship with the anion that forms when it donates that hydrogen, right? When it donates the hydrogen, the anion that forms is the conjugate base. And in videos on the kind of common ion effect, when we were talking about the ions and their impact on pH, we said when this conjugate base is in solution, kind of regardless of where it comes from, if there's hydrogen present, or even if there's water present, then this is going to come and rip away hydrogens from other things, either if it's an acid sitting around just the hydrogen itself, or if it's a water molecule that it hydrolyzes, then it's going to reform this weak acid because it likes to be the weak acid so much. So this solution is going back and forth. These guys are reacting together in the reverse reaction to form this. The weak acid is dissociating, even if it's partially, to form these guys. And when this happens at kind of equal and opposite rates, then we know that we're at equilibrium. Now in a buffering system then, it's not like I have this side is in its own reaction flask and this is in its own reaction flask. This is all happening in the same space. So I have a flask that has all of this stuff in it along with my water molecules. So this is all happening simultaneously. It's not like my arrows here are a boundary between the two chemical systems. So if we think about Le Chatelier's principle and we say, okay, well, here's my buffering system. This is the definition. It's a system with a weak acid and its conjugate base in it. If I was to add, let's add a strong acid like hydrochloric acid. If I add hydrochloric acid to this system, I'm functionally increasing the concentration of hydrogen ions, right? Because as a strong acid, this thing dissociates completely. We have these hydrogen ions in solution. And so what would happen to my equilibrium then? When I increase the concentration of hydrogen, which way is that going to shift my equilibrium to restore the balance? Well, hopefully you recognize that the hydrogen ions are on the product side of this reaction. So when I increase my concentration of products, then it should shift more towards the reactants, right? It shifts left. And this, for those of you who have been studying chemistry for a while, should feel a little bit old hat. We've done Le Chatelier's principle. I know that this is what happens, so why are we talking about it again? Why does this matter? Well, it matters because functionally, I added an acid, right? I added an acid to this reaction. That increased the concentration of my hydrogen ions, but it shifted away from that concentration of hydrogen ions. So I added more hydrogen ions and I got fewer of them, right? That's where the balancing act comes in. That's where the teeter-totter comes in of this equilibrium, because I essentially added an acid to this and it got less acidic as I did so. So there's this, again, I like the teeter-totter seesaw kind of balance to things. I added more acidity, so that should shift the pH to lower and lower numbers. But as I did so, equilibrium kicked in, right? Le Chatelier's principle kicked in, and we have a balance then that is driving this reaction more towards the weak acid and away from these guys. So functionally, as I'm adding acid, it gets less acidic, and the two are canceling each other out. Now, at some point, you're going to overwhelm the system and you're going to add too much of your hydrogen. And at that point, then you're just going to have extra hydrogen left over. You can't react more than what you have present of your anion. So if I have way more of my hydrogen than I do my anion, then it no longer acts as a buffering solution. So it can only do this within certain concentration ranges. But it's kind of a cool feature and it's a little bit paradoxical. Now let's think about our base. Let's add sodium hydroxide. If I add sodium hydroxide, which we know is a strong base, that's that lye or caustic soda, if I add sodium hydroxide, I'm functionally increasing the concentration of my hydroxide ions. Now, if I look at my equilibrium here, it may not be readily apparent what that hydroxide is going to do, unless we know and love water as much as I do. So if I look at hydroxide here, there's no hydroxide in this, but we know that hydroxide, because of the Kw value, we'll look at this hydrogen and say, we should be water. We shouldn't be independent of each other, right? We should be neutralizing each other. So our hydroxide and our hydrogen will react together and form water. So we're functionally decreasing the concentration of hydrogen ions. And when this happens, again, thinking Le Chatelier's principle, so functionally I've decreased the amount of hydrogen that's in solution. So what's going to happen in order to compensate for that? Well, Le Chatelier's principle says if I'm decreasing the quantity of a product, then the reaction is going to shift towards the products to fill that hole, right? So we're decreasing this amount here. The forward reactions rate is going to increase. That's going to shift it right towards the products. And again, if we're taking kind of a 360 view of this, if we're taking a step back from, well, what the heck just happened? Why does this matter? We actually have talked about this before. So why are we focusing on this here for buffers? It's really about a concept check, because again, I'm adding a base this time, which we know would drive the pH towards higher numbers, towards my 14 values. But as I added the base, that functionally took away the hydrogen, which then shifted the reaction towards the products, which then created more hydrogen in solution. So we added more base and it got more acidic. Right? It's kind of wacky, but it makes sense if you understand Le Chatelier's principle and equilibrium. So we added this, we functionally took away our product, and now we had to make more of it. So now the solution is going to push to get more acidic even while I'm adding more base. So essentially, again, kind of like we saw when we added our strong acid, then there's this canceling out. And of course, not in like a mathematical dividing out sense, although we'll get to examples where we're actually using numbers. This is just the concepts part of it. So Le Chatelier's principle says that our reactions in equilibrium are going to shift in order to counterbalance all these factors. If I have a weak acid with its conjugate base, or if I have a weak base with its conjugate acid, right, either way, then we're going to have a system that has this capability. It has the capacity to do this buffering action. We can resist a large change in pH up to certain quantities because of these features, because of Le Chatelier's principle, because of what we can predict about the rates of these forward and reverse reactions when we start to poke at and mess with our equilibrium. Okay, so that's an introduction to the concept. Keep an eye out for some videos on working some problems with buffering solutions, and we'll get to that next.